Good day, Math 30-1s. We continue talking about 1.2, this time referring to stretches. So, vertical stretches occur, like last year, when there is some parameter controlling vertical growth. If I were to say that there is a number in front of some function, we're basically saying that all of the y value is created from some calculation, and then we simply multiply that y value by some value, a. So we could say that there's a vertical stretch by a factor of a. Now there could be a few different things that happen. If we had an a value that is greater than 0 and less than 1, so an a value between 0 and 1, the graph grows more slowly. For example, if I said there was an a value of 1/2, it's almost like there's a restriction of growth. It's making it grow slower, which makes it appear wider. So instead of saying it's wide or skinny, let's say there's a vertical stretch by a factor of 1/2. Some people might say it appears as a vertical compression. But we'll keep this concise and say there's a vertical stretch by a factor of 1/2. Visually, it's a vertical compression. It appears wider. If there's an a value that was greater than 1, what happens is we're calculating a y value and then putting a value that makes it larger. So the graph appears to grow faster and it would appear skinnier. If we said there's an a value of 3, we could say there was a vertical stretch by a factor of 3. I might just say this is a vertical stretch. So vertically we're stretching like an elastic band and looking like we're skinnier. In mapping notation, it's quite straightforward. All of the x, y values are becoming x staying the same, and the y values all have a parameter a that are stretching it or sort of compressing it to a different value. Now, we saw this last year with parabolas, so we'll keep this consistent and familiar. If I gave you a x squared and 3 parameters, a values of 1, 2, and 4, which one would go where on the 3 different parabolas? Now, the one that appears skinniest is actually growing the fastest. So I might pick the a value of 2 and say, yes, it's skinnier, but the effect is that it's growing faster. The next one would have to be an a value of 1 in the middle, and the a value referring to 1/4 is the one that is the widest, but it's vertically being compressed. Vertically, its growth is being restricted. Now, as we kind of continue this conversation about stretches, we haven't really talked much about horizontal stretches yet, but this occurs when the graph has a parameter controlling horizontal growth. Now, like shifting left and right, we are going to have to think a little bit backwards. So we saw this last day talking about a horizontal shift on, say, a parabola, or if I were to just use function notation, some function, we'll stick with x minus 2 squared. This is shifting 2 to the right. When we're talking about horizontal stretches, a similar backwards logic is required. So if I said there's a b value that is between 0 and 1, let's say 1/2, it actually stretches wider. So what's happening is a b value of 1/2 is actually stretching wider by a factor of 2. So we would get to say a b value of 1/2, it is horizontally stretched by a factor of 2. So a b value of 1/2 would appear as a horizontal stretch by a factor of 2. So it's going to look like f of a 1/2 x, and you see the 1/2 x, and this is going to appear as a stretch times 2, stretching it wider. In the other direction, if you had a b value that was greater than 1, for example, a b value of 3, we expect this to be stretching wider times 3, but it's actually getting skinnier. So the effect is that it's going to be horizontal stretch by a factor of 1/3. So you might see this as a 3x, and this is a horizontal stretch by a factor times 1/3. So in mapping notation, it's the opposite effect. If you had a b value of 3, the actual effect is dividing by 3, or timesing by 1/3. There's your opposite effect. So we'll do a couple visuals of what could happen, and I created a W shape, not a parabola, not a radical, not a linear function, just sort of a random function which looks like this. So given f of x below, call this f of x, what would the graph g of x look like if there was, and we'll keep this simple and we'll just say it's a positive 2 f of x. So what would happen if there was a 2 in front of the f of x? Now remember the difference between positions. A in front, B in the bracket. B in the brackets affecting the input, A is in front controlling the output. So if we have a new function g which appears to be a vertical stretch by a factor of 2, we're taking all the y values along here and stretching them vertically up. So this is a y value of 4, we're going to stretch it up to an 8. Here's a y value of 0, it stretches up to a 0. Here's a y value of 2, it stretches up to a 4. Y value of 0 stays at a 0. Y value of 4 stretches up to an 8. And we can call this, that's a 9, stretches up to an 8. We could call this function g of x. H of x, a new one, if we were to do a vertical stretch by a factor of 1/2, we could say, instead of stretching up, we could say it's stretching by a factor of 1/2 and appears vertically compressed. So a y value of 4 stays as a y value of 2. Y value of 0 stays. A y value of 2 times a half is a 1. And if we continue this, y value times a half, we appear to have maybe a new function h, which appears vertically a little bit compressed. Now, maybe just to make this a little bit more interesting, we'll do another function talking about a horizontal effect in just a moment. But let's talk briefly for the domain and the range of g of x. What is the domain of the function g? So talking about left and right domain, where does the function g of x exist? I see it existing from a -4 to a +4. So I can say that all the x values are such that x has to be greater than or equal to -4 and less than or equal to a 4. And we'll throw in a little extra. It's every decimal and fraction in between. The x values are an element of the real number system. So this is saying x values are such that x is greater than or equal to -4, but less than or equal to 4, and all of the x values are an element of the real number system. They're all decimals and fractions. It's continuous. For the y values, if I ignore my error with the positive 9, we would say all the y values are between 0 and 8. All the y values are such that y is greater than or equal to 0, less than or equal to 8, and again it is continuous, and we are dealing with all decimals and fractions as a part of the real number system. What's the mapping notation for g of x? All of the x comma y values are becoming times 2 only on the y values, and so there's an effect on the y values. To make this a little bit more interesting, what if I were to draw a function for you and try to ask what is the parameter affecting it? So if I were to sketch in a different color and ask, what is the effect? Is this a vertical stretch? Is this a horizontal stretch? The hope is that we would see, it is appearing horizontally stretched wider. Maybe by what effect? I could see that it goes from an x value of 2 to an x value of 4, an x value of 4 to an x value of 8. So I'm feeling like maybe some function k of x is being horizontally stretched times 2. Horizontally stretched times 2. So something was happening to the original function f of x, and how do I say horizontally stretched times 2? Now, horizontally is affecting the input, so in the brackets. How do I say horizontally times 2? The actual effect is times 2, so I would need to have a 1/2 as my b value. Quite tricky. As a final question, where do the graphs f of x and y equals 2f of x intersect? So we could, instead of saying 2f of x, we could just say y equals g of x. Where do the two graphs intersect? They intersect. So g of x and f of x, they both intersected. They were invariant on the x-axis. So they were invariant at y equals 0 or on the x-axis. Again, it's this line of reflection, this mirror line, this axis of reflection that work just the same for a stretch as well. And the very, very last question in our chapter 1.2 is trying to interpret a visual. So I've got a function f of x sketched, which is actually x squared. Question is, what is the equation of g of x, and what type of stretch is it? It's a very good idea if you wanted to pause the video and actually attempt to find out what is the effect. Is it a vertical stretch or a horizontal stretch? Many people will see it right away as one or the other. People may look at this and see this point stretching up to this point, or this point stretching up to this point, and say, of course it's vertical. The y value is going from a 1 to a 4, or a 4 to a 16. It's vertically stretched times 4. Others might notice this point becoming this point, or this point becoming this point, and notice the x values in the same horizontal line are going from a 2 to a 1, or a 4 to a 2. Some people might say this is horizontally being stretched divide by 2, or times 1/2. And if we try to articulate this as an equation, we might say that the function g of x is created from f of x, and if we say that it's vertically stretched by 4, we have to put a 4 in front. If we say that it's horizontally stretched times 1/2, we could say f of 2x. Both of these are actually correct. Occasionally you might be asked to determine the value of a or determine the value of b, and it forces you to think down one of these paths. In this case, it was quite open-ended, and we wanted us to think a little bit broadly. Now, how could there be two different equations for one function? Well, the interesting thing about the function g of x and this unshifted parabola is that if I actually replace f of x with its equation x squared, and on the right I replace the input with a 2x, so I change the input to be a 2x, these are supposed to be the same. Well, I might ask, what is 2x times 2x? 2x times 2x is a 4x squared. So in this case, you can actually turn that input 2 into a value 4x to kind of compare the effects. This was a good conversation about stretches, and as we move into our next lesson, we begin to combine all effects, stretches, reflections, and shifts in the same examples. Good luck.